My name is Takayuki Yoshino, medical doctor working on National Cancer Center Hospital East. Today, I'm more than happy to be here and given the chance to present here. So I would like to talk about the clinical value of the virtual sequence. This is a new concept utilizing nationwide cancer genome database. So first of all, I would like to show you the current cancer treatment. There are 4 pillars, including the surgery and chemotherapy and the radiotherapy and immunotherapy. These are very important to patient to be cured or the palliative to prolong the overall survival. So more focusing on the advanced disease, stage 4 and so on. Chemotherapy and immunotherapy and the central mainstay for this advanced disease. So currently, so many pharmaceutical companies intended to clinical development using the chemotherapy and the immunotherapy and so on. So this is a very important curve. This is the survival curve using the Kaplan-Meier curve. You can see this dotted line means the survival rate each time. X-axis showing the time from the treatment. And you can see the survival goes down and goes down, goes down. This means a patient passed away, died during the clinical course, not using any chemotherapy. However, patients received some conventional therapy, a state-of-the-art best treatment to date so far. The patient survival go up comparing to the dotted line. A dotted line means the best supportive care. So, however, 2015, Obama president stated the precision medicine initiative. This means the corresponding therapy for gene X abnormality. This is called the precision medicine. If the patient received such a fit treatment, you can see here the survival rate goes up and goes up, goes up. The some patients be cured even in the patient originally diagnosed for the advanced disease. This is the epoch mating to receive the patient receiving such a precision medicine corresponding drug for the gene X. So we initiated SCRUM-Japan project since 2015. This is a nationwide cancer genome screening project, including the lung cancer, LC SCRUM, and the GI screening. This is the gastrointestinal cancer in turn. There's so many pharmaceutical companies here joining in this project. More than 200 hospitals across Japan also joining in this project. The data center and the administrative office is common across the LC SCRUM and the GI screen. So participating fee from pharmaceutical company was spent by the measurement of the comprehensive next generation sequencing test by the central vendor. This is the overall picture of our SCRUM-Japan project. So to date, this is the achievement for ourselves. You can see here that 30,000 the patient received next generation testing. And you can see here the 300 patient enrolled the clinical trial, either investigator initiate trial as well as a company-sponsored clinical trial. More than 270 hospitals across Japan also be participating. Ongoing clinical trial, 15 ongoing clinical already. The 70 pharmaceutical company included in this project. Of course, the domestic company as well as the international global company also. To date, our achievement here, who approved drugs, who approved companion diagnosis already achieved. And you can see here that all the data, clinical pathological genome data sharing, on-time sharing with academia pharma already achieved. So this is a big, large-scale data set already we created. So, however, one of the big problems, NGS testing takes too much time. You can see 2 to 4 weeks needed to get the result to each patient, because the more than 100 genes, simultaneous measurement of the more than 100 genes. So we spend too much time, 2 to 4 weeks. So brighter future, considering the brighter future, minutes or second level testing will be realized. It's a very excellent news to the patient. So please see, this is the flow of the initiating cancer treatment. Current clinical cancer course, the patient visit the hospital, and then the biopsy to obtain tissue, cancer or non-cancer. We will discriminate this region is cancer or non-cancer. The pathological diagnosis, this is the routine Y, 1 to 2 weeks needed. After that, you can see additional slide is needed for NGS testing, spend 2 to 4 weeks, double score, you can see here. So patient waiting for at least 3 to 6 weeks to start the treatment. It's a very long time for the patient. So I would like to ask you, if your family are diagnosed with cancer, you choose immediate conventional state of therapy, or 3 to 6 weeks later, a precision medicine. Which one do you love here? Here? So you are waiting for the 3 to 6 weeks, a very long time. If you are a cancer, you. That's how long I have to live. Okay. But I guess the best scenario here, immediate precision medicine. No time, no waiting time. It's a very important issue. So I guess the new concept here, the virtual sequencing, if we omitting here, testing weeks, 2 to 4 weeks, omitting this 2 to 4 weeks, this is only in a few minutes or second level. We call this the virtual sequencing. So I guess if the next year, 2020, we achieve the minutes or second level diagnosis called the virtual sequence, will be realized. All patients are happy, I think. So this is a very clinical value of the virtual sequencing. So methodology here, routine way, you can see the hematocrit origin staining, the pathological examination in the routine way worldwide. You can see all the steps, and then the directly diagnosis, genetic alteration, skipping, dissection, and NGS testing. So we use our large-scale database. We now conducting the learned by the training data using our large-scale dataset, and we also created a virtual sequence algorithm, and then validated by the verification data. This step is very important to our data make mission impossible project possible. So this is a preliminary result in our findings for GeneX, which is already used in clinical practice. But it's confidential. We cannot disclose this gene. However, you can see preliminary results show AUC 0.94, which means the near perfect concordance between the real sequencing and the virtual sequencing, I guess. So this is this AUC is a per patient data. So nearly 96% of the concordance we achieved already. So looking at the real NGS sequencing, you can see the cost, thousands of dollars each test. However, we realizing the virtual sequencing, I guess, realizing low cost each test. It's a very important, huge ripple effect on saving cost. So this is the final slide of our SCRUM-Japan Genesis project. This is the first step to use this is a virtual sequence. We have a lot of the database, baseline info, clinical info, specimen info, chemotherapy history, and genomic info, and adverse event, and medical history, and so on and so on. So this database is growing because of the input from the several hospitals updated already. And also, we have a lot of the IT company, Genome, Papare, and the Cloudways and the Google have a chance to use the GCP platform. So I guess the next generation cutting-edge platform on GCP are shifting from another cloud, which will be the monumental way to prove the GCP value and the credibility with a huge ripple effect. So my presentation finished, and moving to the second speaker, the chairman of the Cloudways, Yoshizumi-san, please. Next speaker.
Thank you very much. I'm sorry, I am not so good at English, so now I speak from Japanese. 先ほどご紹介いただきました私、クラウドエースという会社のチェアマンをやっております。私の方からですね、今回のプロジェクトの実際のですね、進行であったりとかですね、今回 GCP を採用した経緯であったりとか、ちょっとテクニカルな部分なんかをご説明したいなと思っております。まず、当社、簡単な紹介をさせてください。当社は Google クラウドプラットフォーム専門の導入支援、開発、運用、トレーニングなどをやっている会社でして、A から始まるクラウドを一切せず、G、オンリー G のから始まるクラウドのみをやっている、そういう会社でございます。逆にですね、GCP 上では、あらゆるニーズに応える形でサービス提供、展開をさせていただいております。要件定義、アセスメントのような上流工程から実装時のコンサルティング、実際の開発、運用保守、支払い代行などなど、トレーニングの提供まで幅広く提供している会社です。140人ぐらいの社員がおりまして、大きな日本のですね、会社さんも顧客に持っているような会社でございます。でまた当社は技術力非常に優れておりまして、日本ではもうトップに近い、世界でも有数のですね200以上の資格保有者有しておりまして、スペシャライゼーションというですね、このGoogle から認めてもらうですね、認定資格というのもこれ7つ持ってまして、2月前半時点では世界でナンバーワン、今だとナンバーツーですね、の会社です。で世界ナンバーワンの GCP サービスプロバイダーというのを目指して、日本だけでなく、アジア各国に拠点を設立して進めている会社です。はい、今日もですね、アジアから総勢15名ぐらいで来ておりまして、この T シャツ着てるものを見つけたらですね、当社の人間ですので、ぜひお声掛けください。はい。そうしましたら、このプロジェクトですね、先ほどいい成果が出せたというふうに、吉野先生から発表していただきましたけれども、このプロジェクト、5ヶ月前の11月から開始されました。でその中でですね、4つ大きな特徴があったかなというふうに思います。まず最初にですね、非常にタイトなスケジュールだったということです。で、5ヶ月前に始まったときに、この場にこうして立つことをまず目標にしようと。サンフランシスコネクストで発表するということをまず目的と、まず直近の目標として、始めたんですけれども、なかなかその中でここに立つためには、1月末のタイミングで、ある程度の成果を出さないといけないということで、実質3ヶ月しかない中で始まったというプロジェクトです。それからですね、大変高解像度の画像ですね、1000人以上の患者さんの高解像度の大量の画像を処理する ために GPU が非常に大変多く使う必要のあるプロジェクトです。また当然なんですけれども、最初始まったときは成果が出るかどうかもちょっとわからないという中でですね、大きな予算は避けず、使える予算が限られているという中で始まっています。また、医療情報ですね、実際の患者さんのデータを使うということで始まっていますので、大変高いセキュリティが求められると、こういうようなプロジェクト背景がありました。本当にいろいろ困難になった大変なプロジェクトでしたけれども、ここに立てていることっていうのをちょっと誇りにしたいなと思っております。はい、で実際のタイムラインなんですけれども、これ、プロジェクトキックオフの時の画像です。で、プロジェクトキックオフ、11月の頭にキックオフしたんですけれども、実際ですね、患者さんのデータを使うというところで、承認がやっぱり必要でですね、それに結局1ヶ月ぐらいかかってしまってですね、さらにそこから実際のデータをアップして、Google クラウド上で扱えるようになったっていうのは、実際12月の後半です。ですので、もう本当に実際、ここまでにある程度、サンフランシスコをここで発表するためには、このあたりで成果を出さないということでいうと、もう実際1.5ヶ月しかないという、本当にもう殺人的なスケジュールをこなしたという形になっています。こんな中でですね、本当にミッションインパッシブルなプロジェクトだということをですね、可能にしたのはですね、本当にGoogle クラウドのおかげだというふうに思っています。最先端の GCP ですね、これがなかったらちょっと難しかったかなと。最先端の GCP を好きな時に好きなだけ使えるというところですね。これ使えない。はい、だったりとか、GPU 好きな世界中でね、大きな規模でもすぐに使えるようにできると。また医療情報を扱うのに十分なセキュリティを確保しており、で、他のクラウドと比べてもコストパフォーマンスという面でも全然問題ないというところで、今回、GCP を採用してよかったなというふうに、考えています。ちょっとそれぞれ、少しずつ触れていきたいなと思います。まず GPU インテンシブというところなんですけれども、このプロジェクト、先ほども申し上げましたけれども、たくさんの遺伝子情報や病理画像を扱う必要がありまして、これらをディープラーニングを使って解析するということが求められておりました。なので、GPU に特化した計算リソースが、大規模なデータセットに対して、適用するで、いろんなパターンで試してみるということが必要でした。で、実際、相当量の GPU を使って、演算を繰り返してきた結果になっています。で、これがですね、実際の、あるプロジェクト、ちょっとプロジェクトが難しいんですけど、GCP でいうところのプロジェクトですね、課金のセットである1個のプロジェクトですね。今回チーム制で、プロジェクトを進めておりまして、その中の一つのチームのプロジェクトの課金のデータ、ちょっと生々しいんですけれども、GPU ユーセージというのがこういう形になっていて、当然使わないときは使わないという形であったりとか、使うときはバーッと一気に使うという形で、やっぱり GPU をずっと買っておいておくというよりかは、オンデマンドで使えるというところは非常に良かったかなと。で、実際この辺はちょっとまだ GPU は日本で使えなかったので、デモデータみたいなことを使って回していたりとかいう形でしたね。で、1月末までにある程度やって、そこからまた精度をどんどん上げていくということをこっちの方でやっていたんですけれども、10分程度で、新しいサーバーすぐ立ち上がったりとか、すぐに使える環境が提供できて、このプロジェクトチームだけではなくて他のチームも含めて、みんなが自由に使えたっていう、すぐに使えたっていうところは、非常に良かったかなと。で、これがなければちょっとこのプロジェクトは、こんなスピードではうまくいかなかったかなというふうに思ってます。はい、またですね、コストですね、リミテッドバジェットっていうところですけれども、 これもですね、ちょっと、先ほどのプロジェクトチームとはちょっと別のところのチームでは、特にですけれども、プリエンプティブインスタンスというのを使って、価格を3分の1に抑えることができました。これ、Google クラウド知ってる人にとっては、そうだよねっていうことかもしれないですけれども、やはり、コストどれだけかかるかわからないっていう中で、プリエンプティブを活用することで、プリエンプティブには途中で、インスタンスが落ちたりとかですね、最大24時間しか使えないっていう、制限がありますけれども、深層学習、ディープラーニングの中では繰り返しエポックで学習モデルを生成していく中でですね、ちゃんと途中で保存するとか、そういった形をすることで、別に落ちても問題ない仕組みっていうのは、これは比較的難しくなく、できるようになっているので、インスタンスが落ちても再度学習できるように工夫をするなどをすると、3分の1にできるという、これも、Google の非常に効率的な使い方なんじゃないかなというふうに思っています。またですね、高いセキュリティですね。このプロジェクト、日本人の医療情報を取り扱っているというところで、非常に、高いセキュリティのサーバーを使う必要がありました。で、またですね、ちょっと、これはこの場で言うのもなかなかあれなんですけど、日本のリージョンを使うということが、やはり、ちょっと日本の中のセキュリティということで、求められているという制約があるという、そういう前提がありました。その中でですね、なので、アジアノースイーストリージョンというのを使わないといけないということがありました。そんな中でですね、アーキテクチャのオーバービューなんですけれども、そんなにすみません、複雑な構成では正直ないですけれども、ローカルのサーバーから、クラウド SDK を使ってデータを、オリジナルバケットにアップしますと。で、ここからですね、ちょっとチームごとに、コンペティションというかですね、いろんなパターンでディープラーニング試してみるっていうことをやっていくのでですね、それぞれチームごとのバケットに分けて、その後、データイメージのクロッピングをしたり、GPU を使って、ディープラーニングをするというのをそれぞれやっていくということをやりました。これもですね、本当にたまたまなんですけど、みんなチームが G Suite を使っていてですね、ということもありまして、もう ID の設定だけで、このオリジナルバケットに対して権限設定をすれば、もうアップロードした直後からすぐ各プロジェクトが、動き始めることが簡単にできたと。ここはですね、コラボレーションというか、みんなで共有して、プロジェクトを推進するっていう中で、もちろんセキュアにですね、当然セキュアにその ID を持った人間しかアクセスできないという形ですぐに始められたっていうのは、これは非常に良かったことかなというふうに思います。これは本当になかったら、ちょっとこのスピード感ではプロジェクトは進まなかったかなと思います。ただですね、ここで、一点困ったことがありまして、日本リージョンに閉じて使う必要があったんですけれども、プロジェクト開始当初というか、12月の時点でもですね、当時、GPU が日本リージョンで使えないということがありまして、これはもう本当にオーマイガーっていう感じで、どうしようっていう感じだったんですけど、ちょうどですね、T4GPU がタイムリーに、日本で使えるように、なりました。アジアパシフィック東京ですね。これはですね、本当に、これなかったら本当にどうにもならなかったところがありますので、日本の Google の安倍さんだったりとか、皆さんが働きかけてくれたおかげなのかなというふうに思って大変感謝しております。もしかしたら、クリスさんも気にかけて、日本を早めてくれたかもしれませんので、聞いてないかもしれませんが、陰ながら感謝申し上げております。サンキュー。はい。そんなこんなでですね、1月16日に使えるようになってですね、実際もう本当にまたここで2週間しかないっていうところで、T4GPU が使えるようになってですね、そんな中で一定の成果が出せたということは本当に奇跡的なことだったんじゃないかなと、今振り返っても思う次第です。はい、その後ですね、ちょっとこのあたりでサンフランシスコこちらで登壇するという発表するということは決まったんですけれども、そこからですね、さらに精度を上げてですね、直前で先ほど出したように 0.94 という成果を出せているんですけれども、これはですね、藤井先生というですね、 日本ナンバーワンの病理医の先生がですね、一生懸命ここでアノテーションであったりとか、データの整理ということをですね、すごく献身的にですね、ずっともう目がめちゃめちゃ疲れて疲労困憊になりながらも見てくれてですね、このおかげで精度がガーンと上げられたんじゃないかなというふうに思います。これは本当に大変な作業だったと思いますけれども、改めて藤井先生もそちらにいらっしゃいますけれども、感謝申し上げたいと思います。ありがとうございます。はい。はい、これが私の方からの最後のスライドになりますけれども、クラウド S としてはですね、今回のプロジェクトを機にですね、もっと野心的な絵を描いています。銀行じゃない、病院からですね、IoT のデバイスであったりとか、今回のデータも含めてですね、さまざまなデータをどんどん上げていってですね、アナライズ、コレクト、ディテクトというところをGoogle クラウド上でですね、非定型なデータだろうが何だろうが、とにかくアップロードして、GCP 上でデータフローであったりとか、ヘルスケア API、ビッグクエリ、ジェノミクス API などなどを駆使してですね、解析して、で、構造化されたデータとして、病院であったりとか製薬会社に使えるように提供できる、そういったビッグデータ解析の基盤として、これから GCP を活用していくことをもっと日本中の病院に含めてですね、広めていくということをやっていきたいなというふうに思っています。でこれらのヘルスケア API であったりとか、ゲノミクス API などなどの活用について、次、アリーさんの方からご説明をしていただきたいと思います。じゃあ、アリー、よろしくお願いします。
Hi, folks. So today, you had a chance to hear from some of our customers and partners about a very specific application, very specific use case that they are solving for. So Yoshizumi-san's team is working on developing this tool, virtual genomics, that essentially uses some data from the medical images, from pathology images, and shows that it's equivalent to genetic information. So that would help save time and help reduce anxiety for cancer patients during diagnosis. And Yoshizumi-san presented how their usage of how their cloud journey has progressed and some of the tools they've used. My goal is to give you a little bit of an overview of how cloud healthcare team, which is my team, is thinking about the space and how we approach the product development in this space. Before I do that, I just want a quick question. How many people here would consider themselves in the healthcare sector? Okay, roughly I see 50% of people. And how many physicians are in the room? Okay. Sir, we know who to call if we need CPR. Thank you. This gives me kind of a sense like where to point this. So let me start from this slide. So this is a paper published by Professor Anupam Jena, who is a Harvard faculty. He's a medical professor, MD. He's also a PhD in economics. And the only reason I bring it up, his credentials here, is that let's assume for a second that he can run a properly designed an experiment. So the experiment that he designed, or the question that he asked, was what happens when American Heart Association organizes a conference? In the US, there are 30,000 cardiologists. And once a year, they go to a conference, usually in San Diego, and a week they're away from their hospitals. 70% of these cardiologists leave their hospitals. Now, something might happen. You know, you look at the data, like who thinks here that the patients got worse during this time? Who thinks the patients got better during this time? So that's actually true. That's what he says in the paper. Like there is data that suggests that if you are hospitalized with acute cardiac condition during the week that all the cardiologists are in a conference, you have better chances of survival. And the data is there. You can take a look at it. He turned to ACC and AHA. He got no comment. The way I interpret this data is that it suggests that sometimes the decisions that are made in a healthcare system are not always in the optimal best interest of the patient, right? We see this through this data. So, and when you look into how healthcare data is used and how healthcare decisions are made, you realize it's very complex, right? And I think that the position we're trying to take is coming from a very humble place here and trying to ask ourselves where technology or where data organization can play a role. Because sometimes it cannot. In an emergency room, you need to make quick decisions. There is no time to look at a computer or look up data information. You need to make judgment calls. But sometimes you can use data in a more effective way. And that's kind of our mission. So what we want to do is to help our customers and partners organize the world's healthcare information. There is a lot of information out there. We see data that imaging data, genomics data is doubling now every several months. So how do we help organize it? How do we make it secure? And how do we make it useful? Right? So secure and accessible, this is kind of the core infrastructure, the core cloud capabilities. And then how do you make it useful? This boils down to analytics and machine learning. So these are like hot themes at every booth you go, you'll hear about it. My goal in this short presentation to give you a little bit more specifics. What does it mean for us in the healthcare space? So when we think about what we are building, like if you ask like what is Google Cloud Healthcare is doing? So we think of our offering as a data platform that is meant to enable providers, researchers to ask and answer new questions using the information that they have. And we think of this platform in 3 layers. There is the data platform. I'll go into each layer specifically. But there is a data layer, there is the cloud services layer, and then there is the applications layer. So let's talk about the data layer first. So the data layer basically means that you have a lot of information. If you're a healthcare provider or healthcare payer or a research organization, you have a lot of information that your machines or your patients is generating. You need some sort of way to organize and manage this information in the cloud. So what we have built and released, right now it's in beta, is a set of services that allows you to manage standard healthcare data types in a fully managed way. So what that means is that we have a DICOM endpoint that runs in the cloud. We have a service that can manage HL7 V2 data. We have a service that can manage FHIR data. So these are kind of the fundamental pieces of any healthcare data or healthcare data set or data warehouse. Now, I'll give this example of a super high-level overview of I wouldn't even call it architecture, but maybe a meta-architecture. We showed a demo at a conference called RSNA, which is the radiology conference in Chicago. It happens every year around Thanksgiving. And what we showed there is basically an off-the-shelf medical imaging device that connects to the cloud. Our cloud can speak DICOM natively, so that means that you can just connect our cloud and ingest any medical imaging modality or medical imaging device. So the data arrives to the cloud, and then from there you can either visualize it using something like a zero-footprint viewer of your choice, or you can run additional computation, analytics, applications on it. In this case, what we have done, we used a tool called AutoML, Auto Machine Learning. I'll talk about it in a second. But we trained a very simple AI model to separate between a hypoechoic and a hyperechoic ultrasound mass. Now, what that means in very simple terms is that we were able to separate water bubbles from air bubbles. Now, it's a simple demo, so this was only shown for demonstration of capabilities of the technology. But we have right now customers and partners that are using these tools to develop clinical applications on real data. So that's the piece I want to communicate here. The other piece is the public data set. So this is especially relevant for researchers. If you're trying to test a hypothesis, then you need to have access to some data to be able to test your algorithm, to test your application. Right now, there is a lot of data sets that are public, in the public domain, but to get access to them, it's not straightforward. You have to download them. It's like oftentimes it's like large terabyte scale data sets. You have to make sure that your tools are compliant and compatible with these data sets. So we want to simplify that task. So we have taken data sets that are already public in the medical imaging domain, in the EHR domain, in the genomics domain, and we host them on our platform so that you can come and test out your tools on the data that is already public in a more straightforward way. So let's say your data is in the cloud, kind of mentally, your data is in the cloud. The question is like, okay, now what? And this is where it depends really what you want to do. The way we see our customers and partners using the services and running on top of their data is in kind of one of these two buckets. One bucket I would roughly call the analytics, and the other one would be the machine learning side. So in the analytics space, this word is probably one of the more overused, especially in a conference like this. So this really depends, like what is the question you're trying to answer? Like for example, if you have an expensive resource, like a physician or a certain piece of equipment that is very scarce, and that creates a bottleneck for your system, you might be interested to see how can I maybe overbook that resource? You know, how many people have in a flight, in an airplane, or in an airport, and you've been offered like, hey, if you have flexibility, we will give you a hotel or maybe $500 so that you can stay and take the next flight. So imagine you could do something similar with an appointment, a doctor's appointment, or a MRI, specialized MRI appointment. So this could be an example of an analytic query. So BigQuery, in this context, is one of our products that enables you to analyze large-scale data, petabyte-scale data. It's an enterprise data warehouse implementation. So the other piece I would mention here is de-identification, especially if you're trying to do some sort of research collaboration. You have clinical data that has protected health information like names and addresses. It has also, a lot of times, things that are not necessarily immediately identifiable, but can help you narrow down. Imagine you're writing, oh, a mother of 10 children in a town, or the CEO of such a company came to visit today, right? So this information is not directly identifying, but it can lead to exposure of PHI. So we have tools that enable you to de-identify data, text data, medical imaging data that are built-in cloud services. Now, this problem specifically, we were very interested to solve this because this is something that we see every research team reinventing the wheel and building their own. And there is always questions I get, well, can your tool detect a pacemaker serial number in a CT image? So in this case, it probably can. There is always the next question is like, well, can it detect a name of a patient that is written on a grain of rice in Sanskrit? Because that's a patient that I had that came to a CT. And the challenge I want to bring up here is that we have data that shows that even when people are doing this task manually, they will still make mistakes. So you cannot devise a perfect tool. So the path we chose is we implemented our tool, and we also connected existing open source tools so that we can offer our customers a choice, and you can compare and contrast on your data, because that's the ultimate test. Couple of things on natural language processing. So we're working with customers that are solving challenges like a trauma patient is rolling in. I have 3 different radiology reports because they had been taken to a head CT and a spinal X-ray and another lumbar CT. And these, because of the different machines, different rooms, they were written by 3 different people. Can I devise a summary that will like very quickly tell me what do I need to worry about? What is the most risky thing for this patient? So this is leveraging heavily NLP capabilities. Anytime you want to use any type of machine learning, you want to have labeled data. So we have solutions for enabling you to label the data that you already have to create labels and to train AI models. Speaking of AI models, here there is different categories of applications. So some applications are kind of operational, like help me predict when I'm going to have a spike in demand so that I can anticipate that and I can maybe invite more nurses. Like if I have an epidemic or a flu epidemic, or if I have, for example, bad weather, more people can end up happening in the ER. So these are kind of on the operational side. Another operational example of analytics is I'm putting a patient in the medical imaging machine. I want to make sure that they're positioned properly so that I don't need to call them again because the test was done badly. So this is an example where the AI can help me identify the positioning. There is also the other side, which is clinical applications. These are more complex, require, of course, more validation to go through FDA. We have customers and partners developing these as well, using some of our tools. So a couple of tools that I want to point out here. AutoML is a tool that allows you to very quickly develop AI models with relatively limited AI expertise. So if you have a team that has access to data, we can show you how to use AutoML to train models on your data. If you have a team that has a little bit more expertise and you want to fine-tune the model, then Cloud Machine Learning Engine might be a better tool for that. So naturally, I would not expect AutoML to produce clinical prediction value models, but with combination using AutoML and using Cloud Machine Learning Engine for fine-tuning, you can get something that can be useful. And finally, on the ML piece, I'll mention that one of the challenges that we see in the space is that a lot of people building AI applications. Some companies literally have like 1 or 2 algorithms, and they're trying to kind of see if there is market for it. So we chose kind of a meta approach here. And what I mean by that is that we are building a tool that would enable you to evaluate different types of AI models. So if you have a model that claims to be able to detect brain bleed, for example, and there is another model that claims to be able to do the same, how do you compare them? How do you measure the performance of them? On the application side, I mentioned a couple of open source tools that we've integrated and enabled researchers to use. So these are some open source viewers that you can run on top. If you store your data in our cloud, you can use these viewers and visualize it, present it for your research purposes. These are some of the identification tools that I mentioned. So Mirc CTP and DICOM Cleaner in the context of medical imaging. This is kind of the best practice. These tools have been written more than a decade ago, but this is still what you see, encounter in practice when people are trying to de-identify medical data. So what we have done is like we built our tool, we integrated these tools with our backend, and we offer to our customers and partners to select and see what works for them best. This is just a screenshot from the AI model browser that I mentioned. The idea would be here that you can select an application and select a data set, and you can evaluate, run this application on top of a data set and evaluate compared to specific applications. We also want to educate the community and help people develop their own AI applications. So we have published several tutorials on how to do that. The example here is like super simple. You will never confuse this with a real clinical application. So we built a classification model for breast density. So the reason it's relevant clinically is that breast density can be a predictor of breast cancer risk. So it's usually scored between 1 means less dense and 4 more dense. And we have created a tutorial that shows how you can use publicly available data set to create a binary classification between 2 types of density. So this is the resource that this is, you can evaluate the performance of the model and you can tweak it. I'll leave this. Oh, actually the link is not here. And not only you can develop this application, we'll also show you how to deploy this application and connect it to the clinical workflow. Because if you develop the best application but the doctor doesn't have access to it, that's a problem. So there are tools that we're working on exactly for this purpose. So this was my final slide. I want to invite back Dr. Yoshino to kind of summarize, and thank you for your time today.
So thank you, Ali. Thank you, Ali. Okay. So thank you very much for the coming. So we would like to summarize this presentation more focusing on the virtual sequencing. So currently, Ali mentioned so many examples of the AI device, but the current device are designed to support the doctor judgment only. However, more considering the virtual sequencing, you can see here, I guess the virtual sequence exceed real NGS sequence in the near future. Currently, we are now communicate between the doctors and the AI. So the AI knowledge also be improve the science level, especially for the pathology. And the pathologists also be input to their curation annotation. So the cooperation between the doctors and the AI is needed to get the surpass doctor in the near future. I'm not sure. But I am confident, based on our experience, a virtual sequence in the near future exceed real NGS sequence. More happy life, I guess. So virtual sequence make a brighter future possible, I think. So prompt accurate diagnosis and optimal treatment enable a global access to quality cancer diagnostic and a ripple effect, the saving costs and so on. So this is our conclusion in my slide. And finally, I would like to show you our SCRUM-Japan Genesis team, and so many Japanese doctors. And he's Dr. Kotani here. Kotani here, okay, he's here. And Dr. Mr. Yamada, he's a Genome Media company. And also the Papare Suzuki, Mr. Suzuki here. And he's a company, Papare. Dr. Fuji here. He's an excellent pathology, and so many members here. Sorry, I'm ashamed of myself. Okay, finally, I would like to thank you for your coming here.